Hi, welcome to the very last part of lecture 4, which is also the last lecture of the core content of this course. Yeah, and in this video clip, we're gonna discuss three tree-based models. Yeah, we will start with single tree. And single tree built using so-called card algorithm, classification and regression tree. And in this part, we will focus only on regression tree, yeah, just to minimize the level of confusion that you may be at this moment, yeah, after so many new topics. Yeah, so we will focus on regression trees. And nice thing about regression trees is that, in contrast to shrinkage methods that I discussed in the previous part, in shrinkage methods, yeah, we are able only to select variables that are the best, but we provide the functional specification. For instance, if we put variables in a linear way, yeah, then any non-linearities, some quadratic relationships or interaction between variables are not detected by shrinkage methods unless we put those non-linearities and interactions in an explicit way as sum of variables. Yeah. However, it is not very efficient. Yeah, and in this way, as you will see in the next cuts, trees are able not only to choose the best variables, but also those methods are able to, on top of this, they are able to detect non-linearities between regressors and dependent variable, and also interactions of very high order between regressors. Yeah, and it is nice that in addition to this, what is really nice in tree-based models, that you can illustrate this in a very nice way, that even people that have very little knowledge about statistical methods at all, they will understand. They will be able to read predictions made by regression trees. Then, yeah, that being said, yeah, so regression trees are cute, but there are some problems that we will try to solve using so-called bugging method, which stands for bootstrap aggregation, and random forests. Yeah, and that's the plan for this part of the lecture. Yeah, and yeah, I believe that we can start now. Okay, yeah, so let's start with an illustrating example, which we're gonna use this data set that you can download from this link over here. Yeah, and this data set, if you download this to your working directory, then you can load this. This is CSV file, yeah, and nbc show details. Header is equal to true. Yeah, and this data set is from this textbook, Business Data Science by Matt Teddy. Yeah, so another example from this textbook. And in this data set, we have some information about perception of pilots of some TV series produced by, I think that all those films belong at this moment to NBC network, Yeah, and in particular, we will be interested in using three variables only. GRP is gross rating points, and this is general impression, yeah, whether viewers enjoyed this show or not. Yeah, there is also genre, yeah, and there are different types. So we will use those variables as regressors, and we will try to explain the variable which really matters for films that want to buy commercials, yeah, during those shows, namely projected engagement. Yeah, and it may sound quite surprising that companies don't care that much about GRP, gross rating points, but rather about projected engagement. Yeah, and projected engagement is whether people pay attention to details during the show and also during commercials. Yeah, so after each of those pilots, people were asked about some details from the plot of those pilots. Yeah, and on this basis, they received average scores from 0 to 100. Yeah, so we will try to build here a very simple model using that we will try to explain projected engagement with GRP and genre. Yeah, so in this illustrating example, we're gonna use a library called rpart, which stands for recursive partitioning. This is another name for card algorithm. And so we can build a tree, rpart, and we are interested in PE as a function of those two variables only. GRP, and data is data. Data is data. Yeah, because it's the same name. Yeah, and we run this. Here, the tree was built, and for this package rpart, in the next part of this video, I'm gonna use package 3, which is used by most textbooks. Yeah, but I used rpart because there is one function that will be useful to understand how trees are built. Yeah, so now if I type rpart plot and our tree, which is type of rpart, we will get 24 tree. Yeah, so this is our tree. So how to interpret this plot? Yes, so on top we have the whole data set. Yes, so those percentage points stand for how many observations are in those nodes, called also, because this is tree. Yes, so those nodes are also called leaves. Yeah, and in the root, in the stop leaf, we have the whole data set. Yeah, and the whole, if we take the whole data set and we don't make any splits, then predictions that is the best for without any splits for our dependent variable, which is PE, it will be 72.68. Yeah, so approximately 73. And now, if depending on some sequence of conditions on our regressors, this prediction is changed, yeah, and this tree is built in such a way to maximize prediction power. Yeah, so we split our whole data set into smaller subsamples to increase our prediction power. Yeah, because if we set this, if we don't make any splits, this will be our prediction, but our prediction power can be improved if, for instance, here we have GRP, if we split our data set into two parts. Yeah, so data GRP, those are different values, and now, depending on whether GRP is greater or smaller, we will change our prediction. Yes, so here, if GRP is smaller than 223, then the prediction for those observations will be 57. And this will be nothing else than basically the average of our dependent variable PE for all those variables that meets this condition. Yeah, so let's compute this. So first I plot this condition. Yeah, we have true, false, true. Yeah, we have a vector that indicates for which observations this condition is met. And now, if we compute the mean of our dependent variable, it will be 57. Yeah, 56.63, approximately 57. Yeah. On the other hand, yeah, so here, this is our final node. We don't explore this data set. Here we have almost 20% of observations, and then there are no additional splits for those observations. But on the other hand, here we have those observations that don't meet this condition. So here we have complementary condition that greater or equal to 223. Here it should be 76. Yeah, yeah, it is. Also notice that here sum of this guy and this guy is exactly 100%. So in the first split, we divide our data set into two parts. Yeah, that overall, yeah, still we have the whole data set. Yeah, but now, given our conditions, we make different predictions. Okay, so here we have our intermediary leaf, and then condition on the fact that this condition is not met, we are here, and then we impose additional conditions. Yeah, and notice that in this data set, we should have, yeah, for type is situation comedy. Wait a moment. Okay, situation comedy is one of those categories. Yeah, so here we have three categories: drama, reality, and situation comedy. Yeah, and here the next split of this subsample goes according to genre. Yeah, and if it is reality show, then okay. Reality show. So I impose that here this is double equal sign. Yeah. you may think that, some of you may think that we will get here 71, but it will be wrong. I think so. Yeah, 64. Why? Because here this node is condition subject to two conditions. It is wrong because here this subsample is subject to this, but also this condition. So we have sequence of conditions. Yeah, so, and now we have 71. Yeah. Also, if we sum this and divide by let's say dim data, we should get 28%. Yeah, because I summed all those guys that meet those two conditions, that doesn't meet this condition. Yeah, so this is complementary condition, and meet this condition. Yeah, so it's 28%. Yeah, and the best prediction for this guy is now 71, not 76. Yeah. On the other hand, if this condition is not met, so we take all other types of shows, drama, so it means that we take drama or situation comedies, we should get 79. Yeah, it is. Yeah, and notice that because of rounding error, yeah, it doesn't sum perfectly to, yeah, those two guys sum to 83. Yeah, so but it's only because of the fact that because of rounding error. Yeah, but all those two observations from those two leaves constitute the higher leaf. Yeah. Finally, this leaf split further into even smaller pieces. Yeah, and notice that here, okay, this relates to this that this condition is not met, because here is also yes, no, yes, no. Yes, so we take this guy, and notice that that here we use this variable again, but so we impose that GRP is greater or equal to 223 and is smaller than 1500s. Yeah, and yep. So if this is met, it will be 78, and if it's not met, also notice that here actually, yeah, it will be 82. Also, yeah, it's small digression, but notice that here all observations that are greater than 1500s also are greater, but automatically greater than 200. Yeah, so this guy and this guy will be exactly the same. Yeah. Yeah. So not a natural question that arises when we get this such a tree is how this tree is built. Yes, so essentially the algorithm is quite intuitive. Yeah, and so the algorithm proceeds in the following way: that first we take our whole data set, and then it considers all variables and all values for each variable. For each possible split for each variable, the algorithm splits the dataset into so-called left dataset and left leaf and right leaf. Yeah, for left leaf, we put all observations for which variable is smaller than some cutoff value, which is also chosen by the algorithm, and on the right we have all observations that are greater or equal for this variable. Okay, and now, so let's assume now that here we have only one variable. Yeah, and let's see how this 223 is actually computed. Yeah, so this is what we're gonna do right now. So yeah, so the algorithm will choose this split for this variable for which residual sum of squares after the split and assigning average value of dependent variable after the split is the lowest. Yeah, so this is this goal function of this algorithm. Yeah, so let's try to do it manually only for variable grp. Yeah, so first let's create a vector of this is vector of all unique values of grp, and let's sort it. Yeah, so here we have this, and now we will create a loop to first split so here we will compute what's the MSE for each potential split. Yeah, depending, so we're gonna vary this value between 7.5 and 2700. Yeah, and and we will see what next. Yeah, so here we have this from 1 to length of this guy, and now the prediction. So here we consider all those potential splits, and now our y left, this will be the average for those average data PE for which data GRP is smaller than considered value. Yeah, so this will be our left prediction for those that go to the left leaf. Right will be this. Yeah, so this is complementary condition. And now prediction for all variables, let's call it forecast, will be depending whether GRP is smaller than this. If this condition is met, we will take while left. Otherwise, this condition is used. This value is used. So we have forecast, and then we are interested in computing mean squared error for this forecast. So what we have to do is to take data PE minus forecast, raise this to power of 2, compute mean, and this will be our MSE first split. We repeat this for each possible value. Okay. Notice, for the algorithm chose value 223. And now let's plot MSE first split against values. Okay. Here we have this point for this guy, for variable GRP, this value of split will generate the lowest MSE. Okay, so if we take which mean MSE split and compute and choose these values, yeah, it is 232. Yeah. 220. Okay, it's 232. Here we have 223, but notice that it will bring the same result, yeah? Because here and there are no observations between those two values. Yeah, so any value from interval between this and this will do a job. Yeah, and most likely I think that, to me, it looks like the average of those two guys. Yeah, just yeah, exactly. Yeah, so this value is not uniquely defined. Yeah, but yeah, this split is the one that maximize here, that any split from this interval minimizes the MSE, yeah, and improves prediction power of this split in comparison to the initial value of naive prediction of 73. So now we're gonna use another example, and we will use different package. Personally, I'm a fan of rpart, yeah, but in most textbooks, instead of rpart, package 3 is used. Yeah, so including our textbook Introduction to Statistical Learning with Application in R. Yeah, so we will use library tree, and the reason why I'm using this that it allows to perform cross-validation a bit easier than using rpart. Yeah, so just for your convenience, I will do it once again using using dataset Boston from package mass. Yeah, and here we're gonna use tree. We will create object tree Boston, and the structure is quite similar to for LM models. Yeah, that here we provide what is our dependent variable. We put all possible regressors from dataset Boston. Yeah. Okay. And it runs exactly the same algorithm, but yeah, if we want to plot this this tree using command tree, we cannot use rpart plot, but we have to plot tree Boston. It will generate something like this, and then we put text tree Boston. Yeah. So here the problem is that we don't get intermediary nodes. Yeah, it is, in my opinion, yeah, it is not so nice as the previous package. Yeah, but yeah, it is used in our textbook, and yeah, but it's not that important. What is important that here the algorithm chooses in each split, they choose different variables. Yeah, from time to time it chooses the same variables for different cutoffs. Yeah, but overall, yeah, here we have many interaction of different variables. Yeah, and this result is endogenously generated by the cart algorithm. Yeah, so this is it. The problem with trees is that with single trees is that they very often overfit. Yes, so they suffer similar problems like with those models that are too complicated, and they perform very well inside the training set, but outside the training set the prediction performance is relatively low. Yeah, and some solution to this is to try to conduct so-called pruning procedure. Yeah, that we will prune some of our branches using cross-validation procedure. Yeah, and pruning procedure, first we conduct cross-validation procedure, CV Boston, and there is this function CV3 that conducts cross-validation for us. Yeah, so it determines what's the best number of final nodes. Yeah, I don't want to get too much into details about this, but the philosophy is super similar to lasso or ridge regression. We won't code this here manually because it may generate unnecessary confusion amongst you and maybe even me. Yeah, so let's use this CV3, and now this object provide here here we have number of final leaves. Here, for instance, in the full tree, before cross-validation procedure, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is the maximum number. And then, using cross-validation procedure, this algorithm chooses this, which for which this is impurity measure, this deviation that the lowest is the best. So if we plot CV Boston def and we plot this against size, we will see that the lowest value for this particular case is for the whole tree, yeah, for 9. In the previous example, we discussed how tree algorithm detects interaction between variables, because notice that in previous example we had some sequence of conditions depending on different variables, yeah, and maybe so here we have, for instance, to get to this node, here we have to use interaction of values for variable this, lstat, and rm. Yes, so in this way, yeah, that's a nice thing about trees, is that, yeah, it detects interaction between regressors. That's the first thing. Another thing that now we're gonna study will be detection of non-linearities of the impact of regressors on the variable of our interest. Yes, so in this exercise we will play a role of data gods once again. Yeah, and why? Because it will be nice to I think that for exposition reasons, yeah, it will be nice example. So let's create detection of non-linearities, and if you want to have the same results as I have, set seed to value equal to 100, yeah, and let's create dataset consisting of 100 observations, and let's create data frame with variable x. Okay. Here we have, at this moment, we have one variable drawn from normal distribution, yeah, and we can create another variable in this data frame which depends on some crazy nonlinear interaction, nonlinear relationship, and so I created the following example. So there is sign, but on top of this there is also some positive trend and some noise. Okay. Yep. Yeah, so this deterministic part, if we want to plot this deterministic part, let's create this, maybe even from this interval length out. If we substitute this with this, yeah, this is relationship. Also, I should, yeah, this is this relationship which is super nonlinear, yeah, and it's not obvious how, yeah, so this is our relationship, this deterministic, and we would like to, from data points that we observe, we would like to recover this relationship, but what we observe is something like this. Okay, so those are our data points, and now we will use tree just to see, yeah, what we get. Yeah, so actually let's okay, this is true value, and now if we want to fit our tree, but yep, actually we can type this tilde dot to use all variables, yeah, or even we can use x, but let's use dot. Okay, and here we build, yeah, a lot of conditions depending on values of x. We have only one variable, yeah, and but we can, but now, okay, and now we would like to use our exec to predict the value from our tree using those exec values. Yeah. So for this end, we have to create new data set, because in prediction tree we have to predict. We provide object tree and the data set. Yeah, so here we have to provide. We have to create data frame x. This is the name of the variable that will be used by tree, and here we will provide those sequence. Okay. Yeah, this is our x, and now we would like to make prediction on y. So we create new column y, which is predict tr, and yep, we provide this. Yeah, so it made prediction for us. Those are fitted values from our tree, and now we are in the position to plot the result of the fitted value for our tree. Yeah. Let's use color. It's tree with leaves, so let's use green color. Okay, you see, this is that. Actually, this one tree, it's not great, it's not bad as well. Yeah, so it could be worse, it could be better. Yeah, but overall, yeah, I think that as the first approximation, it may be better. It may be not that bad. Yeah, so this is example how a single tree is able to detect some non-linearities between x and y. The problem with single trees is that it provides predictions that are not continuous. Yeah, here changes, small changes in x's, even for a smooth relationship, yeah, will end up here in very different predictions. Yeah, and on top of this, yeah, the single tree is very sensitive to changes, to small changes in datasets, in training datasets. Yeah, so even though that trees are nice because it can be illustrated in a very nice way that even people with no statistical knowledge at all can understand the message of trees very quickly. In terms of prediction performance, it's not the best. And what is much better is to use, instead of single tree, the whole forest, yeah, and many trees that that each tree is trained using slightly different data set. Yeah, so it's like for each tree we sample different data set and then we average predictions made by all those trees. Yeah, this procedure is called bagging. And it stands for bootstrap aggregation. We didn't discuss bootstrap in this course here, but it's quite intuitive. Yeah? So instead of one tree that provides predictions, here we will have, for instance, 1,000 trees. Yeah, and in this particular example, we will use package ranger and to build many trees, we use the following syntax. Yeah, that we say that we want to explain why, using all variables, our data set is df and number of trees is equal to 1,000. So, yeah. So this, now we have new object with 1,000 trees, and now we can each tree, so for each prediction of of this data set. For each observation, we will ask each of our 1000 trees what's the prediction for this particular observation. And then we take our final prediction will be the mean of all predictions. And you will see that actually it's quite efficient. So let's create rpart while back, and we make, let's do it this way, back 3 predict back, fit, and here we provide our object ranger. In some textbooks people use package random forest, but ranger is exactly the same, but it is much faster. Yes, so in all your examples in real world, use ranger package instead of random forest. Yes, so here we make prediction back trees, and we're gonna use this, the rpart. Yeah, so okay, and now if we plot prediction of our forest with against observations against observed values of x's. Let's use color orange. Yeah. No, not orange. Red. Okay, invalid. Okay. And now the problem is that I forgot about this. Here, to extract predictions, yeah, it is list. Yeah, so we have to use this outcome of prediction with. We have to call this explicitly. Yeah, it's not very intuitive. Yeah, I don't like it. Yeah, but this is how it is coded. Yeah. Okay. You see, it's a bit, I would say, first, for sure it is smoother, yeah, than one single tree, yeah, and for 100 observations, yeah, it's a bit better, yeah. So let's repeat this exercise, but with 1000 trees. Okay, and let's see what happens. Okay, we have more observations here. If we make predictions only on those guys, and so actually it's quite nice, I would say. Yeah. So this is so the conclusion of this exercise is that while single tree, it may be not the best predictor, a forest, an ensemble of many trees that are for which predictions are averaged out can be nice improvement over one single tree. Yeah. So now let's compare prediction performance of bugging and a single tree, and also random forest that I will introduce now, on the dataset that we know, Boston, and yep. And we will evaluate prediction performance on some test set of observations that were not used in training models. So to this end, we have to split our data set into training set and test set, just like we did it before. Okay, so now for each observation we have assignment whether this observation is used for building our models or for testing the quality of our models. And for tree, it will be, we're interested in this dependent variable, and the dataset that we're going to use is Boston, but only those observations that were sampled to be in the training set. Okay, and now bugging will be just like before. Here, and now what is important is that there is parameter mTry, which tells us how many variables in a given split are considered for creating this split. So before we had only one variable, so always only this variable was used. If we use, here we have 14 columns, but one of those columns is medv, this median value. And so if we type 13, this method, this ensemble of trees, this method will be called bugging. And so it will, this will be bugging, and the only difference between random forest and bugging is that on top of this, on top of this, not only random sample of observation is used for building a single tree from many different trees, but also a random sample of variables. And why we do it? This very simple trick will lead to generating decorrelated trees. If we have one regressor which is super important, it may be so important that it will lead to the situation that only this variable will be present in all trees, and those trees will be super similar to each other, even though that they were built using different observations. Yeah, so what is recommended is to use for random forest, and that's the only difference from bugging, is that not only random subsample of observations is chosen, but also for each split random subsample of variables. Yeah, and here there are different rule of thumbs which says how many variables it should be, but let's use mtry equal to 6. Yeah, so less than half of those observations. Also, there is one option's importance impurity. If we provide this after building our random forest, we will be able to plot, to generate a plot of variable importance. Yeah, and we will return to this soon. So, okay. Last but not least, let's use also one of shrinkage methods that we learned before to compare prediction performance between lasso and those three methods, and we will use glmnet and also to make cross-validation. So to choose the best model, we're gonna use cvglmnet, and before we used sparse matrices, but here we have our dataset Boston, which is a data frame, and to put this inside a glmnet function, we have to use the structure that we already learned from best subset selection of variables, model matrix. Yeah, so I forgot to mention this in the lecture on the shrinkage methods, so sorry for this. Yeah, but I'm doing this right now. Yeah, so I create this mistake. There should be no, it's okay. I created this model matrix that now I can provide as the arguments for cvglmnet. I choose only those observations that are in the training set, and also notice at Boston here our dependent variable is the very last column. Yeah, so our y, the second argument, will be what? Those observations that are in the training set in the very last column. Yeah, so this is it. Alpha is equal to 1 because this is lasso. Lambda, let's use those values, and let's use tenfold cross-validation. Okay, has been computed, and now let's make prediction for each of those models. Lasso predict will be what? Predict so lasso Boston, this object, on all observations that are not in the training set, and as the best this lambda that we're gonna use will be the result of cross-validation. In our case, it will be this. Okay. Yep. So we make lasso predict, and yep, this is it. Tree predict. This will be Boston, and here we can use data frame. Yep. Okay. Random forest prediction. It will be the same, but what's the name for this? RF. Okay, sorry. Here it should be RF Boston. Yeah, so I forgot to change this. Yeah, so I created bugging Boston twice. Yeah, so let's do it. Let's go. Yeah, sorry for this. Okay. Now this is it. RF. Yeah, everything worked. So here we put RF Boston. Okay, and now, so we have prediction for all for each of our models here, and to complete MS lasso, we have to take Boston from this Boston dependent variable from our test set. We take lasso predict, we raise this to power of 2 and take mean. Okay, this is it. Make prediction for our tree, we have to change what? Only this. For banking, it will be this. Sorry, it won't be this because this predict here is of this size here. As I said before, it's weird. We have to type predictions. This is a feature of the prediction procedure for object generated by random forest or ranger. Yes, so this is it. Okay. Yep. Yes. So. Let's print this. For lasso, it's a bit smaller than 20. For tree, it's larger than for lasso, and there is substantial improvement over single tree and lasso with bugging, and this tiny trick with random variables, with a random subset of variables, also improves prediction of random forest in comparison to bugging a bit. Yeah, so from time to time it is much better. In other cases, yeah, it's not that, yeah, but it's better to use random forest than in general, as a general rule. Yeah, random forest seems to perform better than bugging method. Yeah, so again, I would like to notice that, yeah, so even though that a single tree is even worse than some other methods, other methods like lasso, but an ensemble, a collection of many models that can be that may suffer from overfitting may be just fine, and yeah, because random forest is a collection of many trees and many of them are overfitted. Yeah, but on average, if we average predictions made by those single trees, you will get a result which is substantially better. Yeah, so this is it. Yeah, and the very last thing is that here I provided importance that we use impurity, and here, and then the nice thing is that if we train random forest or bugging using this option about importance, then we can evaluate the contribution of each of those variables from the dataset, which increased the performance of random forest. Yeah, I don't want to discuss this in this course here because this is only bachelor course. Yeah, it's not that difficult. Yeah, but at your stage, it's not necessary to understand this. Yeah, but one day, why not? Yeah. So if we want to illustrate this, let's sort this from the most important to the less important, and using bar plot or box plot, bar plot. Yeah, we can get plot of those variables that contributes the most to improving quality of our random forest. Yeah, so I think that, yeah, so this is it about random forest. Okay, so actually this concludes my lecture. Yeah, the intention of this course was to first familiarize you with programming in general, yeah, and we used R here, and also to organize a very quick helicopter tour over I would say nowadays classical machine learning methods, yeah, and I completely understand that for many of you, those concepts can be very abstract and not intuitive at the very beginning, yeah, but with machine learning, it's to some extent similar to mathematics. Yeah, John von Neumann once said that in mathematics, at the very beginning, you don't understand something, and after some time, you start getting used to it. Still, you don't understand this, yeah, but you are more you feel more comfortable with using all those objects, yeah, and I believe here that it's nowadays it's really time to invest some time in learning much more sophisticated methods, yeah, but more or less, yeah, the whole philosophy is not very different from those concepts that I try to explain to you in this discourse. Yeah, so good luck in your exam, yeah, and hopefully, yeah, I hope that I convince you that those methods are worth further exploration in your future professional or academic endeavors. Yeah, so have a nice night. Yeah, for me, it's after midnight.
Town in this less than fashionable cubbyhole of the San Francisco Examiner, these editors are programming today's copy of the paper into that same Ohio computer. When the telephone connection between these two terminals is made, the newest form of electronic journalism